So the first discussion is the so-called Morera's theorem. This is basically the inverse for the reverse for the Cauchy integral theorem, which now saying that now this region F, if you define all the loop, so C sub 1, C sub 2, all loops, the basic is the reverse. If you have all loops C sub I, F, C, B, C, within where C sub I are all the whole loops are within this region of space. So you have a certain, define a certain domain or given a name or whatever. If they are all for C sub I, then F is analytic. So it's kind of the other way around for the Cauchy integral theorem, which, as you can imagine, which is a very difficult to apply. You check all the contour before you determine whether F is analytic or not. It could be useful for mathematical argument, but for practical check whether F is analytic is quite it's not easy, right? So, but you so just basically for your knowledge, you can do the inverse of the theorem. But your textbook try to prove it, which I'll basically let you read it. But during this proof, he introduced this equation 11.34. So basically, all this, the concept that a loop integral is zero is like independent of paths within this loop, so C sub 1, your point A to point B. Saying that going around the loop is zero, it's just like it's just the same as saying that all the path integral from A to B, say A to B along 1 or 2 along 1 is the same as A to B along 2. Like, okay, accept that because the loop is zero, then this path, this value from A to B is independent path from either from 1 to path 1 or path 2 or any path that connecting A or B, right? So that is fine as long as so that's the point of confusion. This statement is coming from the first statement. All the C sub i's are within this region. So you need to maintain all the paths still within this region. And because this is to argue that F is analytic over this region, as long as all the curve, all the loops are within this region. But basically, this statement is also true if all these paths connecting A and B will not go outside of the region where F is analytic, right? And this statement you can write like your 11.34 in the textbook. Basically, is saying that this actually writing this on the right hand side doesn't matter. Since 1 to C sub 3 are A and B of FC, BC. Basically, that means this is independent of path, which means it's a function of endpoints at C sub 2 means that is 1. So that's your equation 11.34. Right. Can you recognize what is this? If this is real function, what do you call this? Remember your calculus. there's a name for this equation. If now it's going back to real function, these are real numbers. What do you call it? Forget all the calculus. This is called the fundamental theorem of calculus. Fundamental. You forget about the most fundamental thing about the calculus. And there's one more thing in here. So fundamental calculus is we're saying that this f is the so-called the anti-derivative of f, which basically is saying that f prime is maybe right. Basically, right. Combining these two is called the fundamental theorem of calculus. What now? So this argument is true for even for complex function, but the confusion or the I mean the mistake that sometimes you forget the restriction that all these paths. This is actually a path integral for complex integration. This is saying that it's independent of path, so we don't need to specify the path. So and then we can still show that this is the f, capital F is the anti-derivative of f. So basically f, the derivative of capital F is derivative of little f, right? So you still have that, but all these are within all the path that is within the region of where little f is anything. So first you need to define a certain region R where f is anything. Then with for all the path within this region, then this is true, but not for the path that get outside. Say if you have a singularity somewhere. Right, draw it the other way. So you have a singularity somewhere in here. So outside this region, then the paths they connecting A and B. Then if you go the other way around, so first you define this R. If you go outside of it, then this may or may not true, right? Especially when the path cause a singularity. Say this obviously is not true when you go going around. This path going around a singularity, then obviously this will be different. This will no longer be independent of path. So this path 1 to A to B, or C sub 1 to C sub 2, C sub 1, C sub 2 is different from going this path. Right? Right? Because if it's because of the singularity, then no longer you can argue that this loop is zero. If this is your loop in the Cauchy integral theorem, this loop is not zero because of the singularity. So therefore, this path integral A to B along this path is different from this path. So this becomes dependent on path comparing these two paths. So you cannot write it as just a function like that, or if you write it like that, this becomes, you can actually say that this f becomes a multi-value function. So say from A to B, this or C sub 1 to C sub 2, these f C sub 2, when you go along this path, you get one value. When you go along this path, the other path that going around the singularity, get you another value, a different value. It's basically like a different branch of a multi-value function. So therefore, you need to be careful when you apply the fundamental theorem of calculus. That's okay. So sometimes you forget about that, and then you do do a path integral from one point to another point. You just write the antiderivative, and then just like what we do in the wheel function, and forget about whether the path is actually go outside of the singularity, and that will get you into trouble. I say, okay, so need to be a little careful.